BGP can carry 1 million routes and still deliver the wrong service to one tenant. Scale is therefore not a route count. It is controlled distribution, the correct address family, the correct policy, the correct visible paths, and the correct next hop at every receiver. Route reflectors reduce sessions, but they also make selection and visibility less obvious. The rejected assumption is that a scalable control plane is merely a smaller, full mesh. It is not. The core learning is this. MP-BGP scale comes from deliberately constraining who can exchange, import, select, and forward each kind of reachability. Here is our agenda. First, prove that both peers negotiated the required address family. Second, identify the reachability and next hop information carried by the multi-protocol attributes. Third, follow a route through import policy, preference, selection, and export policy. Fourth, examine what a route reflector makes visible and what it can hide. Fifth, distinguish path advertisement from local multipath and preserve the data plane next hop. Finally, test the resulting service through reflector and path failures. The sequence matters. A route cannot be correctly reflected if it was never validly exchanged or admitted in the first place. Multi-protocol BGP does not turn one neighbor into one undifferentiated stream of routes. The base session uses the ordinary BGP finite state machine. Each additional network layer protocol is identified by an address family identifier and subsequent address family identifier. Capability negotiation states which families a peer can exchange. Policy and route state are then evaluated per family. This is why IPv4 unicast may work while L2 VPNE VPN is absent. The session is shared. The contracts are not. Operationally, record the global session once, then record negotiated capability, route counts, policy, and failure states separately for every required family. A speaker advertises multi-protocol capability in its open message. The capability identifies an AFI and SAFI. For EVPN, the assigned pair is Layer 2 VPN, AFI 25, and EVPN, SAFI 70. Both speakers must advertise support for the same pair before that family is exchanged in both directions. A route reflector must enable the family on every relevant client session as well. Do not infer this from configuration text alone. Inspect the negotiated capability at both ends. If the pair is absent, the correct result is no EVPN-NLRI, even though the global neighbor is established. MP_reach NLRI carries three things together: the address family pair, next hop information, and reachable NLRI. MP_unreach NLRI carries the family and withdrawn NLRI. An empty MP_UNREACH can also serve as an end-of-RIB marker for that family. The attributes provide a transport framework. The family specification defines the meaning of the NLRI bytes. EVPN then adds route types, route distinguishers, Ethernet segment identifiers, MAC, and IP fields, or prefixes as appropriate. A packet trace of the BGP update should therefore be decoded in layers: BGP attribute, AFI and SAFI, EVPN route type, then route-specific fields. A received route enters a conceptual adjacent RIB in. Inbound policy may reject it, alter attributes, or assign local preference. The decision process considers eligible paths and places selected reachability in the local RIB. Outbound policy then determines what is offered to a particular peer. Implementations may not store 3 literal tables, but the questions remain distinct. Was the route received? Was it admitted and selected? Was it advertised to this client? A single show command rarely answers all three. For a route reflector, add a fourth question. Was the selected path eligible for reflection under the client and non-client rules? A community is policy metadata. A standard community is a 32-bit value. An extended community is an 8-octet structured value. Neither changes forwarding, merely by existing. A policy or protocol procedure must interpret it. This distinction prevents magical thinking around tags. A community may cause a route to be preferred, rejected, exported, or imported, but only because a defined rule says so. Record the value, the policy that matches it, and the action applied. In EVPN, route targets are a particularly important extended community use, but they remain an import and export mechanism, not a tenant identifier that independently programs a VNI. The route distinguisher is part of VPN-NLRI and makes otherwise identical routes distinct. The route target is an extended community used by import and export policy. The VNI is a 24-bit data plane context carried by VXLAN. One service may use all three, but each answers a different question. Which route instance is this? Who should import it? And which tunnel context should carry the packet? Reusing the same decimal number can be convenient, yet it does not merge the semantics. Troubleshooting must inspect all three independently, especially when overlapping tenant addresses make an RD necessary and controlled shared services require multiple RTs. A scalable policy system makes permission explicit. For external BGP, RFC 8212 defines a fail-closed default in which routes are neither accepted nor advertised without configured import and export policy. Whether a particular release enables that behavior by default must still be verified. Inside an EVPN fabric, the same design principle should be applied deliberately. Admit expected route types and attributes. Import only intended route targets. Constrain unexpected defaults and set route count safeguards appropriate to the platform. Negative testing is essential. Remove a required policy and confirm the route disappears. Introduce an unapproved RT and confirm that no tenant forwarding state is created. Traditional internal BGP does not advertise an IBGP learned path to another IBGP peer. A full mesh works around that propagation rule, but session count grows quadratically. A route reflector changes the rule for configured clients. A path selected from a client may be reflected to other clients and non-clients. A selected non-client path may be reflected to clients. Originator, ID, and cluster list help prevent reflection loops. This reduces client sessions dramatically. It also makes the reflector a policy, selection, and visibility point. The reflector should distribute VTEP reachability. It should not become a VTEP or alter the intended data plane destination merely because it carries the routes. A route reflector participates in path selection. It normally reflects the path it selected, not every path it received. A client may therefore see one path, even though the reflector knows several valid alternatives. This is path hiding. It matters when clients have different IGP costs, when multi-homing offers several egresses, or when local multipath requires more visibility than the reflector supplies. Redundant reflectors do not automatically solve it if both make the same selection. The design must decide how much path diversity clients require then prove what they actually receive. Session scale is valuable, but invisible alternatives are part of its cost. A DD-PATH and ECMP solve different problems. A DD-PATH is a negotiated BGP capability that allows a speaker to advertise several paths for the same NLRI, each with a path identifier. Local multipath is an implementation decision to install several eligible next hops in forwarding state. A DD-PATH can improve visibility without producing ECMP. ECMP can exist locally even when only one path is advertised onward. For EVPN, verify support for the specific address family and release before relying upon ADD-path. Then inspect 3 separate counts: paths received, paths selected or retained, and forwarding next hops installed. Equality among those counts is not guaranteed. In a common EVPN fabric, a leaf advertises an EVPN route with its VTEP address as the BGP next hop. The route reflector distributes that route while preserving the next hop. Another leaf resolves the advertising VTEP through the underlay and sends the VXLAN packet there directly. The reflector is control plane transit, not data plane transit. Rewriting the next hop to the reflector can make service routes resolve toward a node that neither terminates the VNI nor owns the endpoint. Verify the next hop before and after reflection, its underlay recursion, and the resulting tunnel object. The path of the update and the path of the packet are deliberately different. 2 route reflectors do not prove redundant service. Remove one reflector session and measure what remains. The surviving session must retain the required family capability. Required routes must remain imported and selected. Their next hops must remain the original VTEPs and resolve through the underlay. If Graceful Restart retains stale paths, confirm that the retained forwarding really survives. Otherwise, stale control plane state can hide a black hole. Restore the reflector and observe route churn and path stability. Repeat with the other reflector. The acceptance claim is not that both sessions usually exist. It is that losing either control plane distribution path does not remove or misdirect the service. The core learning is this: scale is controlled visibility, not merely fewer sessions. For one representative route, prove the family capability, the received path, the import decision, the selected and reflected path, the preserved and resolved next hop, and the resulting packet. Repeat the proof after losing either reflector. Add negative evidence. An unnegotiated family carries no routes. An unapproved route target imports nothing. A hidden path is not mistaken for forwarding diversity, and the reflector never becomes an accidental tunnel endpoint. Do not trust the architecture diagram. Select one route at one leaf and trace exactly how every other leaf learned what it now believes.